Hello everyone, welcome to our Mechanics of Materials online lecture classes. I hope every one of you are doing very well. Today I am going to discuss thin wall pressure vessels. Basically we will know what kind of stresses are developed in a thin wall pressure vessels, and so the pressure vessels are very ubiquitous in everywhere you can see. So this is one example. I think this kind of pressure vessels is is very popular in, you can find it in the car shop. And so this is a compressor and there is a cylindrical pressure vessel. Basically this vessel is used to store the compressed gas. And this is another example of pressure vessels. Those kind of vessels, if you see, these are the cylindrical and these are the spherical. So these pressure vessels are used for storage petroleum, for example, like petrol, diesel, and LNG, or even sometimes they use for storing the water or any other petrochemical in a large scale. And so we are going to discuss what is called the first we will discuss what is thin wall. So thin wall pressure vessels is, let me adjust the so thin wall pressure vessels. So if I take a cylindrical vessel, if I cut the cross section, so this is my radius, this is R, and this is thickness. I define this thickness T. Thickness is T, and so the radius of the vessel, say R, and thickness is defined by T. Now if R, ratio of R and T is less than or equal to 10, then we call that vessel thin walled pressure vessel. So today the theory I'm going to teach is valid for the thin wall pressure vessel in which the ratio of radius and thickness is equal or less than 10. Now let's consider this pressure vessel. It has a fluid inside and its internal pressure is P. And I'm taking a segment here. This segment I'm taking here, and this segment is thickness is width is dx. So this is an imaginary segment I cut. This is called cut out a hoop, and if I draw it here, say this is my segment. Okay, so this is a hoop, and say this hoop, so the width is dx. Okay, now now I take this hoop and I cut into half, and I got a semicircular section. And you see this blue is actually a fluid, and this white circumference actually the wall of this tank, and the radius of this cylinder is r, so the diameter is twice r, and the thickness of the wall is r. Now this pressure, as you know, that there is a pressure, internal pressure actually exerted on the wall of the cylinder. So this pressure is P, and it is acted on this segment, and so to counter this pressure, there are two forces actually which counter these pressures, and these forces is F by 2 and F by 2. Now if I take if I draw a force balance in x direction, equal to 0. Okay. Now, so let me draw this here. So this is the thickness, this is the force minus F by, so F by 2, F by 2, this is my pressure P, and this is X, this is Y. Okay, now so if it might do, this is F by 2 minus F by 2. So this pressure is acted on a strip which is twice r, which length is twice r, this is twice r, okay, and this width is dx, this width is dx. So as we know, there is F P is equal to F A, force into area. So that's why my force balance here, I'm going to try it again. My force balance here is minus F by 2 minus F by 2 plus P into twice R multiply Tx is going to 0. Okay. So minus f plus 2p r dx is going to 0. That means f is equal to 2p r dx. So this is my equation number 1. Now so the f is twice prx, and what is the area? So there is another area. So if this is the thickness of the film, this f is acting on this one. Okay. Now if I take the cross section of this segment, actually this, let me draw a better way. So this is force F by 2 F by 2, and this is, if I cut this section, and cross section of this is okay. So this is the F by 2. Now this length is dx, and this length is the t. T is the thickness. T is the thickness of the wall of pressure vessel. Okay. T is the thickness of the wall of the pressure vessel. Now, so as you see, the force is acting on this face. The area of this face A is equal to T dx, right? But keep in mind there are two areas. One is here, one is here, the other here. So the total area actually multiplied by 2. 2T dx. T dx multiplied by 2, 2T dx. Okay. Now, so this force is normal to this face. This force is normal to this face. That's why the stress generates due to this force is normal stress. Okay, and we know the definition of the normal stress. For example, say this is sigma 1 is force divided by area. Okay, so from equation 1 we learn that force is equal to 2p r dx. Okay, and area equal to area A is equal to 2t dx. Okay, so I can say sigma 1 equal to PR divided by T. Since normal stress is equals to pressure, internal pressure inside the cylinder multiplied by radius of the cylinder, and this radius is the inside radius and T is the thickness. So this stress as you see in this picture, this stress is act along the circumference of this cylinder. So that's why this stress is called circumferential stress. It is also, there are other few names. Most popular is, this is called hoop stress. From now on I am going to call it hoop stress, and it is also known as tangential stress. Also known as girth stress. So circumferential stress, hoop stress, tangential stress and girth stress all are the same, and it is defined, can be calculated by the internal pressure multiplied by the radius, internal radius of the cylinder divided by the thickness of the cylinder. Okay, so now if you look at this picture here, this sigma 1 is directed to the circumference, and if you look at this, the strip, hoop strip, actually it acts on these circumferential direction. Okay, now let's consider another scenario. Okay, if I have this cylinder and the pressure is acted on this, on the cross section, pressure is acted on the entire cross section of the cylinder. Okay, and now because it acts on the cylinder or on the entire cross section of the cylinder, so there is a stress actually oppose this pressure. So you see this, the white line, white arrow are the pressure, and because of this pressure there is an opposite, there's a reaction stress comes out from this strip of this cylinder. Okay, and now we can say the resultant force, we can say the resultant pressure force, we can say resultant pressure force we can say P multiplied by cross-sectional area pi r square. Now because of this stress, there is a, because of this pressure, sorry, there is a resisting force of tank valve and this force is sigma 2 multiplied by A. And remember, the sigma 2 is the force, is the stress, this reactionary stress due to this pressure. And we know this area is twice pi r t. This area is actually the circumference of the cylinder multiplied by thickness of the cylinder. Okay, so this is F. So we can, if you do the force balance, this resultant pressure force P multiplied pi r square is equal to resultant resisting force, which is sigma 2 multiplied by 2 pi r t. So sigma 2 equal to P r by twice t. Okay. So we got two stress equation. One is sigma 2, the another one is sigma 1. Okay, the another one is sigma 1. So this sigma 2 is a longitudinal stress. It's a longitudinal stress, and sigma 1 is hoop stress or circumferential stress or tangential stress. Now, if this is an element on this cylinder, so the sigma 1 act on the circumference and sigma 2 act on the longitudinal axis of this cylinder. If you zoom this element here, as you see, the sigma 1 is acting on the transverse direction and the sigma 2 acting on the longitudinal direction. But if you look at these two equations, sigma 1 and sigma 2, it says sigma 1 equal to, so if I take this equation and if I can multiply it by 2 in the both sides, 2 sigma 2 equal to P r by T. Okay, so I can say 2 sigma 2 is equal to, and we know P r by T divided by T is equal to sigma 1. So we can say, or sigma 1 is equal to 2 sigma 2. So we draw that conclusion from this relation, and this conclusion is very important, that hoop stress is 2 times of longitudinal stress. Hoop stress is 2 times of longitudinal stress. Okay, and that statement is very important. Now, and I'm going to tell why this relation or this statement is very important. So this is a pipe, long pipe. It carries water and it carries high pressure water, and because of the high pressure there's the tube here, this pipe or tube actually burst. Now if you look at here, this rupture, and you see these ruptures and these ruptures, in all the cases the ruptures are parallel to your longitudinal axis, parallel to your longitudinal axis. None of the ruptures occurs in other way, but I'm trying to actually discuss here is if I draw a cylindrical vessel, and I have an element here, and this is my sigma 1, that means hoop stress, sigma 1, and this is my sigma 2, which is longitudinal stress. And as I said, the sigma 1 is twice as the sigma 2, so this element actually stretches in this direction more, because sigma 1 is greater than sigma 2. That's why the element here, if it is a rectangular, if it is square, if the square element turns out a rectangle, stretches, because it stretches in this direction more than compared to this direction, right? So as a result, we will see fractures, we'll see the rupture like that. Okay, we will see ruptures like that because it stretches in that direction, because they stretches more in that direction. The ruptures occurs which is parallel to the longitudinal. This is my longitudinal axis. Okay, this is my longitudinal axis. Okay, this is my longitudinal axis, and you never see a failure. It is very highly unlikely to see a failure like that. This kind of failure we will never see this kind of failure, and this we always see the ruptures in the longitudinal direction, as you see it here, 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 and here. So that's why when you want to design a pipe, cylinder, any pressure vessels, you have to figure it out what is the longitudinal stress, what is the hoop stress, because your design will be based on hoop stress, which we will discuss in the next few slides. Now, as I said before, there is another type of pressure vessel is spherical pressure vessel, and let's look at the spherical vessel. This is a spherical pressure vessels, and I'm considering a segment here. I cut this spherical pressure vessel to a half, and this spherical pressure vessel has an internal radius of r and the wall thickness of t. Okay, the wall thickness of t. Now, interestingly, the spherical pressure vessel, so if this is a P, the pressure is acting on this cross section, and because of this pressure, so there is a resultant pressure, as I discussed in the cylindrical case also. There is a resultant stress, and this resultant stress is sigma 2. Now, same, if we go to the resultant pressure force equal to P pi r square, and resultant resisting force of the tank wall F is sigma 2a, which is sigma 2 twice pi r t. So if we do the force balance, this P pi r square is equal to sigma 2 pi r2. I can write sigma 2 equal to P r2 t. So what does that mean? That means that in the cylindrical is spherical pressure vessels, only longitudinal stresses are involved. You can the wall experiences only the longitudinal pressure stresses, the sigma 2, and in both direction, in this direction and also this direction, there is no hoop stress. Now, because of that, the spherical tanks can contain higher pressure fluid than the cylindrical tank. I'm repeating this one. The spherical tank contain higher pressure fluid than the cylindrical tank, because spherical tanks do not experience any hoop stress. Okay. Now, so and the spherical tanks and the cylindrical tanks, if you go any petroleum plant, you will see that cylindrical Tank usually is comparatively in less pressure than the spherical one, and usually the cylindrical tank contains liquid or like a diesel, petrol, or the cylindrical plant. On the other hand, the spherical uh, tank contains light gas or high pressure gas like LNG. So this is an example of LNG. All the LNG tank throughout the world, actually it has a lot of spherical tanks, and in, in a moment we are going to solve a problem, and after solving this problem we can easily understand what is the advantage of spherical tank over the cylindrical tank. So this is an example 8.1, and it's in the book page number 24112. So it says that a cylindrical pressure vessel has an inner diameter of 4 feet and a thickness of ½ inch. Determine the maximum internal pressure it can sustain so that neither its circumferential nor its longitudinal stress component exceed 20 ksi. Under the same condition, what is the maximum internal pressure that a similar size spherical vessel can sustain? So we are going to solve that problem. Let's solve that problem. Then you will understand the advantage of spherical pressure vessels over cylindrical one. Okay. So is given the sigma max is 20 ksi, and the first we are considering for the cylindrical pressure vessel. And the diameter of the cylinder is given, internal diameter D is 4 feet. So that means radius is 2 feet 24 inch. Okay. Now we learned just a few minutes ago, for cylindrical pressure vessel, the maximum stress occurs in the circumferential direction. Okay, so that means, in other words, hoop stress is the maximum stress, and we know the hoop stress sigma 1 is equal to PR by T, and we can say sigma, say P is equal to sigma 1 multiplied by T divided by R. So we know that sigma 1 here is the maximum stress is 20 ksi multiplied by thickness, or we also know the thickness T is equal to half inch by half inch. R is 24 inch, so that is 0.4166 ksi P, which is 400, so it is equal to 417 around ksi psi. Kilo pounds inch square, I multiplied with 1000 to convert it for psi. So since 416.66, I am writing 417 psi. Now, okay. Now look one thing. The internal pressure is 471 psi. Okay. So the fluid inside the cylinder is exerting pressure which is 417 psi, and the stress, the maximum stress is developed due to this pressure is 20 ksi. If you divided 20 ksi by 417 psi, that means 20 plus 10 to the 3 psi, 417 psi, which says 47. That means for internal pressure and internal pressure P is equal to 417 psi, the stress, the maximum stress development is 20 ksi, which is 47 times higher than the internal pressure. So I think you understand that how much this small pressure, so for 470 psi, it generates a stress of 20 ksi, so which is 47 times higher. Now consider the second case, spherical vessel. Okay, in the spherical vessels, the sigma max is also 20 ksi, D is also 4 feet, so R is equal to 2 feet, is equal to 24 inch. T is also the same, half inch. Okay. Now we know the spherical vessel. In spherical vessel there is only one stress, that is longitudinal stress. Sigma 2, and sigma 2 is PR by twice T. So if I rearrange this, the P is by sigma 2T by R, which is 2 into 20 KSI multiplied by half inch divided by 24 inch. So P is 0.833 KSI equal to 833 PSI. Okay, so the P. So these are the two results. So the one is this P for the spherical one is 417 psi, and pressure for the cylinder is 833 psi. That means spherical pressure vessel will carry twice as much as internal pressure as a cylindrical vessel. So you may ask then, why are not all the pressure vessels are spherical instead of the cylindrical? You may ask this question. For example, you may ask that the pictures I show first here, why this one has cylindrical instead of the spherical? Because it can withstand more pressure. The reason is, making a spherical vessel is more expensive and more complex than the cylindrical vessel. So usually cylindrical vessel is preferred where the internal pressure is low, and the internal pressure can generate such a stress that can withstand that can be withstood by the materials of the cylinder. But if it does not, then spherical pressure vessels is preferred. So I hope you have understand the concept of thin wall pressure vessels. You have a good understanding of the hoop stress and the longitudinal stress, and why hoop stress why the advantages of spherical vessels over the cylindrical vessels, and how to calculate the internal pressures and the hoof stress and the longitudinal stress. So please listen to these lectures carefully, and if you don't understand, ask me a question. I also encouraged you to read the book. It is in this chapter 8, from page 409 to 411. So please, this is a very important engineering concept. Um, you, I'm pretty sure in your future life, you'll see a lot of applications of the hoof stress and the longitudinal stress. So take preparation for the quizzes. I will send email about how to take the exams, and the syllabus already they gave. I gave to you in my last one of my last email. So stay healthy and be safe.